Hi friends, so let's dive into the mechanism of action of enzymes. Have you all gone to ATM? So you might have gone there, and if you want money, what you will do, you have to put the ATM card in the correct position so that you are getting the money out of it, right? So even the ATM machine is a big thing. You have to put the card in the correct position, then only you will get, and you have to put the correct pin also. That's another story, but still you have to put the insert the card in the correct slot. Like that, this enzyme can be considered as a big three-dimensional structure, which is usually a protein. Some non-protein part are also there, but generally it is a protein. It's a three-dimensional shape is there for the protein. Now, in this protein, there is a small pocket or a crevice, so that or that crevice is what is called as the active site. Now, when the substrate is coming, this substrate should bind to this crevice or the pocket. Now, this crevice is what is called as the active site. Just like the example that I've told you in an ATM machine, you have to insert the card in the correct slot. Just like that, the substrate should come and bind to the pocket, which is called as the active site. I hope the concept of active site is clear to you. So what we are discussing here is, you can see here, this is the three-dimensional structure of the enzyme. And in this three-dimensional structure, you can see a crevice or a pocket here. And this crevice or a pocket is called as the active site, and the substrate should come and bind to this active site. So what is formed is an enzyme substrate complex. Okay. So we are going to give a definition for this active site. Active site is a crevice or pocket in the three-dimensional structure of the protein. The protein is the enzyme where the substrate binds. Okay. Once the concept of the active site is clear to you, I hope it is clear. Now we are going to see what happens in a uncatalyzed reaction, which means if there is no enzymes helping in that reaction, then how the reaction is progressing. Okay. So for that, what we have drawn here is, on x-axis, the progress of the reaction, which is called as the reaction coordinate, and on the y-axis, the free energy, Gibbs energy. What is given here is the free energy. Okay. Now, this is the reactants or the substrates. So here what you can see is the free energy of the substrate. So that is what we call, or what we write as, GS, which is the free energy of the substrate or the reactant. When the reaction is happening, this reactant should attain certain energy so that it should reach a point here, which is called as the transition state. Then the free energy, you can see it is coming down, so that this is called as the free energy of the product, termed as GP. Okay. Now in this, what is marked here is the difference or the free energy that a substrate has to acquire so that the reaction can happen. So only if it reaches the summit, the reaction will happen. So that energy, this energy is called as the activation energy. Activation energy is the energy or the free energy the substrate or the reactant has to acquire so that the reaction will take place. Or in other words, we can write the products are formed. So this is called as the activation energy. We usually write it as E act, which means it is the activation energy. Now, the next thing that we should understand is that there is another term called as delta G, or otherwise we call, like under standard condition, we call it as delta G0. Delta G0 is called as the free energy change. Free energy change. Now, this free energy change is the free energy of the product. So delta G0 is free energy of the product minus the free energy of the substrate. Now, if the delta G is negative, or delta G0 is negative, then this will be a thermodynamically favorable reaction. So it is a thermodynamically favorable reaction. So the difference between the free energy of the product and the substrate is called as delta G0, otherwise the free energy change. So what we have learned here is the substrate has to acquire certain energy so that the products are formed. The difference between the free energy of the product and free energy of the substrate is called as free energy change, or delta G0. Delta G0 says that it under certain standard condition, the free energy change, we call it as delta G0. And activation energy is the extra energy that the substrate has to acquire so that the products are formed. I hope that's clear. Now, what is the action of an enzyme? What we have seen is an uncatalyzed reaction. Now what we are going to see is what happens if there is an enzyme. So here what is shown here is the substrate here. This is the product. So in an uncatalyzed reaction, we have already seen that there is this is the free energy. Now this has to acquire certain energy, which is called as the activation energy. This is it, activation energy, that is E act, and this is of an uncatalyzed reaction. Okay, so that the products are formed. This is an uncatalyzed. But what is the advantage if there is an enzyme? The advantage is that if there is an enzyme, this transition state which I have told you, this is the transition state that the substrate, the energy level that the substrate has to acquire is lowered. Or in other words, what we can see is this is the reactant has to acquire energy only up to this, so that this difference, see, this difference is the activation energy of E act, which means activation energy of a catalyzed reaction. It is the activation energy of a catalyzed reaction. So if you see, it is less, which means enzymes lower the activation energy. So I'm writing here, enzymes lower activation energy. Now we have seen in the prior reaction, there is something called as free energy change. That is what we have written as delta G0. What was that? It is the free energy of the product minus free energy of the substrate. Now that was marked here. It is the delta G. So under standard condition, we call it as delta G0. Now, whether this is catalyzed or an uncatalyzed reaction, is the delta G0 changing? No, which means the free energy change, which is delta G or delta G0 under standard condition, remains the same. It remains the same. Or in other words, enzymes do not affect delta G0, but it's lower the activation energy. Here we should also learn that is this is a previous year question. There was a reaction coordinate given and asked which of the following is an enzyme catalyzed reaction. So I will just tell you some of the examples where the reaction coordinate should not be like this. So what we have seen is a reaction coordinate where the substrate is going like this. Okay, so this is the activation energy. So this is the usual. This is the reaction of the free energy of the product. This is the free energy of the substrate. This is a reaction coordinate. Now, I'm going to draw another diagram here where you can say I'm not marking the free energy and the reaction coordinate because already you know that. So if we get a picture like this, is it right? No. Once this has reached here, this is the reaction like this, the free energy change of the product. Now then it will not go up like this. So this is wrong. It will not go up like this. It should be like this. So this is wrong. Number 2, if you get a picture like this where energy is acquired, then it is going below this reaction like the lower level. This is also wrong. It will not go below this. It should be above this. So you have to correct. The correct should be like this. So it should not go below this x-axis. Okay. Then one more is, if you get a picture like this, where you can see a reaction coordinate like this. Will it go down? No. This is also wrong. So it will not go down. It will not go below this x-axis. It will not go up. See, once it reaches the product level, it should be like this. It should not go up. It is also wrong. So if you are getting a picture, an image-based question, you have to note all these things when you answer such question. This was a previous year question where it was an image was asked and asked which is the correct enzyme catalyzed reaction. So that is the shape of the, already I have shown you, this is the shape of an enzyme catalyzed reaction. Okay, what we have seen is lowering of activation energy is the mechanism by which the enzymes favor a reaction. So how the enzymes are lowering the activation energy? So that concept can be explained using this picture. You can see this is a picture of a hill. You can see it's a picture of a hill. So if there is a person here who wants to cross this hill, what he has to do? He has to reach the summit. Then he has to descend down. This is what you have. What he has to do. Okay, can we make this a bit easy for him? How can we make this process easy for him? That is what is shown in this picture. If we are able to make a tunnel in this mountain, then this person for this person there is no need to climb over the hill and then descend down. He can just cross over using this tunnel. This is the action of a enzyme, right? Enzyme lower the activation energy. So when enzyme wants to lower this activation energy, it has to overcome certain energy barriers where it is always not favoring that reaction. So enzymes are coming, it is lowering those energy barriers, or just like making a tunnel in this mountain so that the reactants can easily become the products, right? So what are those energy barriers and how the enzymes are crossing over those barriers? That is what we are going to see now. So I'm writing first energy barrier and how the enzymes is lowering the activation energy by crossing this energy barrier. Number 1 is entropy of the system. Entropy of the system. Okay, what do you mean by entropy? Do you remember the physical chemistry classes that we have learned in +1 and +2? Oh, we have all forgotten that, right? I will just tell you what is entropy. Entropy is called as randomness of a system. Randomness of a system. For example, if you are sitting in a classroom, it is like a proper order is there in that classroom. Sometimes what happens, if the teacher is giving you a break, then if the teacher is giving you a break, then you will all go out. So that state where you are going out of the class when you are getting an interval or a break, that is called as the randomness or entropy. So during the break, this classroom is having high randomness, right? Because everybody is disorderly placed. There is no order in the system. That is called as high entropy or high randomness. Okay. Now, when the bell ring, or if the teacher comes into the class, what we will do? We'll all gather inside the classroom and sit in proper places. Now, this is called as the disorderliness is, or the state is called as disorderliness, or the randomness, or the entropy of the system is lowered. Okay. Now, what is the action of this enzyme? The enzymes lower or decrease the entropy of the system. So that what will happen, all the reactants is coming in the bond forming distance, so that the reaction or the collision frequency and the reaction, the possibility of that reaction to take place is high. So that is one way whereby the enzymes is making a tunnel in this huge mountain. Okay, now we are going to the second thing. That is, if this is the enzyme, okay, we have the substrate here. Around the substrate, there is a shell of hydration. Especially, if the substrate is in a soluble state, we know that solubility means that the particle is surrounded by a shell of hydration. So if there is a shell of hydration around the particle, it is soluble. Okay, fine. Uh, but what is the problem here? If the substrate has to bind with this active site, then the shell of hydration should be going, or it has to be removed. Or I will just compare the shell of hydration as the negativity always surrounding you. In your state, you might be thinking that I'm not going to crack this PG entrance. It is very difficult for me because I have lots of other works in my family. I have a lot, I have financial problem. I have problem with my like thinking process. I have no time to study. I have to work and study. I have to make money. So many negativistic thoughts are there surrounding you, which is hindering you from binding to this active site. Okay, so what you have to do, or what is the action of this enzyme? The enzymes, it is desolvating the substrate, so that these negative thoughts is like dissolved. So what will happen, once this negative thoughts are dissolved from our mind, then the substrate can go and bind to this active site. Did you get that point? So it means that the enzymes lower the activation energy, or the enzyme is building a tunnel in this mountain by desolvating the substrate. So the second is desolvation of the substrate, where the shell of hydration is removed. The third process is, or the third mechanism where this tunnel is being built, is proper alignment of, or the energy barrier, if I'm writing improper alignment of the enzyme and the substrate. Okay, how can we overcome this barrier? By proper alignment. Okay, so this proper alignment is explained by various theories. That is what we are going to learn now. So the first theory is the Emil Fisher's template theory. We can learn this with a simple story that we all know. It's a fairy tale that everybody knows. It's a story of a Cinderella. Now, in the Cinderella story, the Cinderella was wearing a glass slipper when she danced with the princess in the party. Once when she has to, when the clock struck 12, then she knows that she has to get into the pumpkin caravan. So she ran and she lost her glass slippers. Then the courtmen were in search of the lady who danced with the prince the whole night, because the prince fell in love with the lady whom which she danced with. So they were in search of this lady, and they reached the Cinderella's house as well. But the sister, like the Priscilla and Anastasia, they couldn't wear the glass slippers. But Cinderella was there and she could wear the glass slipper. Why? Because her feet is complementary to this glass slipper, which means that this is what is called as Emil Fisher's template theory, which says that just like a lock and key, for every lock there is a particular key. Only with that key you can open this lock. Just like that, for every enzyme there is a fixed shape for this active site, and on this fixed shape of the active site, only a substrate which is complementary to this active site can bind, just like the Cinderella wearing the glass slippers. So this is what is called as the Emil Fisher template theory. It says that there is a fixed shape, actually the fixed three-dimensional shape for the active site, so that only a substrate complementary to active site can bind. So this is also called as the lock and key mechanism. But what is the problem here? This theory cannot explain the dynamicity or the dynamic changes that accompany a reaction, cannot be explained here. That is the problem with Emil Fisher's template theory. So, there is a second theory that was put forward by William Jenck and Linus Pauling. This can be explained with a simple example of stick and stick case. So, this is a stick. Okay. Now, when the stick is breaking, we know that the first state will be like this, where the stick actually will bend. So, this state is called as a transition state. Okay. Now, the third stage is the stick is breaking into products, or I will say that this is the sticklet. Okay. Now, if we have an enzyme here, the first example that I am giving here, this enzyme, we give an interesting name to this enzyme. This is a stick case enzyme. Okay, stick case enzyme wants to break the stick. Now, if the active site of the stick case enzyme is complementary, so this is actually, it is complementary to the stick. The complementary to the stick, then less products are formed. So this is Emil Fisher's theory. But William Jenck and Linus Pauling are saying that it is not complementary to this stick, but this enzyme is actually complementary. The active site of the enzyme is complementary. Complementary to what? The transition state. So that the transition state is the one which is binding to the active sites, or the complement. This active site is complementary to this transition state, and their observation is that if the enzyme is complementary to the transition state, then more products are formed. So this is called William Jenck and Linus Pauling theory, which says that the active site is not complementary to the stick or the substrate. It is complementary to the transition state. Now this is the second theory, but yet again there was a there was a further modification in this theory, that is it is replaced by another theory which is the most widely accepted one for the proper alignment, that is the uh, theory put forward by Daniel Koshland. Daniel Koshland is saying that, or this theory is called as the induced fit theory. That name itself is telling you what is it. So we will just learn with the example. We in this picture, what you can see is a pair of glove. So if this pair of glove is worn by Mickey Mouse, it takes the shape of a Mickey Mouse hand. If the same gloves is worn by a Donald Duck, it will take the shape of a Donald Duck's hand. Similarly, there is no fixed shape for the active site. When the substrate come and bind to this active site of the enzyme, then it induces some conformational changes in the active site so that the reaction will happen. This is what is given. So I will explain it with a picture here. So Daniel Koshland's induced fit theory says that when the substrate come and binds to the active site, you can see that it is not perfectly complementary to the active site, but when the substrate binds, you can see this enzyme, when it enzyme changes its shape slightly, so that when the substrate is entering the active site, it causes a conformational change is induced by the binding of substrate to the active site. Okay, so what you can see here is the products are formed. So this is the most widely accepted one. This could explain the dynamic changes that accompany a reaction. Can be explained. Okay, so what we have been discussing is about the proper alignment. First, we discussed about the Emil Fischer. That's an old theory which is replaced by William Junk, where it is saying that it is not complementary to the substrate, but it is complementary to the transition state. And the third one is like it is not complementary exactly to the substrate, but when the substrate bind, it induces a conformational change. So these are the three theories of the which explain the proper alignment of the enzyme towards the substrate. So once we have learned the theories that lower, which explain the proper alignment, we are going to see how the enzymes, or what are the different mechanisms by which the enzymes are lowering the activation energy. So we have learned the energy barriers which are crossed over by this enzyme, and what is the various energy barriers and how can the enzymes overcome these energy barriers we have seen. Now we are going to see which are the mechanisms by which they are going to lower the activation energy. That is, one is called as, just know the names only, you don't have to learn in depth about all these things, because sometimes if a question is coming, some in the options you will be giving, they'll be giving these names. So for that sake only I am giving this. Just have an understanding, a superficial understanding about what are these. That's enough. Now the first mechanism is catalysis by proximity. Is that word telling you something? Catalysis by proximity. It says that when the reactants are coming in bond forming distance, then reaction will take place. That is called catalysis. So enzymes are actually favoring the reactants to come in the bond forming distance. This is what is called as the lowering of entropy, where the randomness is reduced. The enzymes, the reactants are all coming in the bond forming distance. So there is one more name that is given to that process, which is called catalysis by proximity. There is no proper example for that. Almost every reaction is like this only, where the reactants are coming in the bond forming distance. That is called catalysis by proximity. They should come proximal to each other so that the reaction can occur. That's it. Then acid-base catalysis. The name is telling you something. Yes, you know what are acids and what are like bases. So acid-base catalysis means that in the active site there are some certain amino acids in the active site which are called as the catalytic residues. So this active site, or in other words I will write the catalytic residue Catalytic residue is nothing but certain amino acids in the active site. I've told you what is an active site. So in the active site, there are certain amino acids which is like the highly reactive amino acids in the active site. So this catalytic residue in the active site is acting as an acid or a base. What are acids? Acids, they are proton donors. Bases are proton acceptors. Okay, so certain catalytic residue act as proton donors or proton acceptors so that it is facilitating this reaction. That is called as acid-base catalysis. The example is aspartate protease enzyme. Aspartate protease. One example of aspartate protease is pepsin, which is in the digestive system, which digests or lyse the proteins. Fine. Then another mechanism, or the named mechanism is called covalent catalysis. What do you mean by covalent catalysis? The name is saying something about it. That is, the covalent catalysis says that the substrate binds to the active site by forming a transient covalent bond, which means when the substrate is binding to the active site, a transient covalent bond is created between the substrate and the product. So this is called as a transition state, where it is not like a permanent one, it will break later. So this is called as covalent catalysis. So this covalent bond formation, or this transient covalent bond formation, is facilitating the reaction to occur. Okay, so this is example is serine protease. Serine protease. Do you know any examples of serine protease? We all know it. That is, they are trypsin, then chymotrypsin, elastase. All these are examples of serine proteases. This is the mechanism. There is a covalent catalysis. Then metal ion catalysis. This is for certain metalloenzyme, where this metal is the hero here. Metal helps in the alignment of the enzyme towards substrate. Enzyme towards a substrate. So is there any example here? So definitely it should be a metalloenzyme, right? We have learned the examples already. Zinc in carboxy peptidase, where zinc is the hero which aligns the like the enzyme for the proper reaction to occur. Then catalysis by strain. Strain is something which is like we are making the substrate strain so that the substrate is breaking. Okay, so catalysis by strain means that the enzyme strain the substrate in such a way that it is facilitating lysing of the substrate. So this example for this catalysis by strain is that it means that once the substrate bind to the active site, it strain the substrate so that it is breaking a bond. Okay, so what will be the example for it? The example should be all the lytic reactions. Lytic reactions, there are two enzymes, lyases and hydrolases. These are the two lytic reactions where the substrates are like the two substrates are what you can see is that there is a bond breaking that is happening where the substrates are converted to two products like that, or that is what is called as, or that is a reaction mechanism in the lytic mechanism, which is called catalysis by strain. Fine. So these are the various mechanisms. So in this part, you no need to dive deeply into it. I just explained the superficially what are they, and just know the name and what is it, what is the example. That itself is enough. Whatever I have told you is enough for you. No need to dive in depth of these mechanisms of enzyme activity. So to summarize, what we have learned is, we have learned what is an active site. Just learn the example, that is ATM card into the correct slot, so that we are getting, so that slot where we are putting the ATM card is the active site. That is a simple example. Then what we have learned is the reaction coordinate of an uncatalyzed and a catalyzed reaction. Enzymes lower the activation energy. So what we have seen is, we have compared it with a hill, where we can see that enzyme is building a tunnel so that the reactants can easily cross over this mountain. So this energy barriers are overcome by the enzymes. So one energy barrier is decreasing the entropy. Second is desolvating the substrate. The third is a proper alignment. To explain the proper alignment, I have explained the three theories under that. Then we have learned which are the named mechanisms whereby enzymes is lowering the activation energy, where we have learned catalysis by proximity, catalysis by strain, acid-base catalysis, metal ion catalysis, covalent catalysis. Okay, so that is about the mechanism of action of enzymes. So to conclude, I just want to tell you this: falling down is how we grow. Just think about our childhood, where we have fallen down many times, but we strived to that through that period, and now we are walking, we are running, we can do so many other things. So just like that, if we fall down, it is not an indication that we are failing. Falling down is actually a stepping stone to success. But staying down is what make us die without any growth. So if we fall down, don't stay down there. Stand up, get up, and we have to move forward, just leaving behind all the setbacks that we have, and all the circumstances we think that it is, we are not going to do it. Or in other words, just from what we have learned in this theory portion that we have learned in mechanism, just desolvate those negative energy and get up, move forward. So thank you.